Physicists just announced that they've slowed down time by 30 minutes, using a tiny crystal that's smaller than a sesame seed. And while it sounds like science fiction, it's real science. The findings were published last week in the prestigious journal Nature. But before we go further, let me clarify one thing. There is no way you or I will ever be able to slow down time at will. It's not possible, however. Learning about how scientists manage to achieve this can teach us something new about the universe, and may help us do all sorts of things we never imagined, like faster computers, better encryption algorithms, or even time travel. Time crystals are made from a material called a supercooled liquid, which is basically a liquid cooled below its freezing point. You see, normally when you cool a substance, you're removing energy from it. As that happens, the particles within it slow down and eventually come to a halt. At this point, they're locked into a rigid structure and the material becomes a solid, but certain liquids can be cooled further without becoming a solid. They remain liquid, but only just. These substances are incredibly sensitive to vibrations and other disturbances, so much so that scientists used to think they didn't actually exist. But then in 2017, a team of physicists led by Cornell University's David confirmed that they did. They created a supercooled liquid from a type of matter known as a superfluid, and unlike regular fluids, superfluids have no viscosity, meaning they flow without any resistance. This particular superfluid was made from a gas of rubidium atoms, cooled to just a few nanokelvins, above absolute zero, the coldest temperature possible. It's literally as cold as it gets. Absolute zero represents the complete absence of thermal energy. It's S when a material has zero heat, and its atoms are at their lowest possible energy state, and not moving. In theory, reaching absolute zero would completely eliminate disorder in a system, resulting in perfect order. But what does any of this have to do with slowing down time? Well, in 2018, another group of researchers led by Mikhail Lukatsky at the University of Basel in Switzerland made an incredible discovery. While studying a supercooled liquid under a microscope, they noticed something strange. It seemed like some parts of the liquid were oscillating back and forth in perfect sync. And after carefully examining these oscillations, they realized something groundbreaking. The atoms in the supercooled liquid had formed a repeating pattern, kind of like a crystal, only it wasn't a solid ball. All the atoms were still moving around, just in a highly coordinated way. The researchers named their discovery a time crystal, because it seemed almost alien-like. We're used to thinking of crystals as being made of atoms or molecules arranged in a regular repeating pattern, like a geometric shape. And usually crystals are solids. But the time crystals seem to combine the orderliness of a crystal with the seemingly chaotic randomness of a fluid. In fact, time crystals appear to break the very definition of what a liquid is supposed to be. Typically, the atoms in a liquid are in constant random motion, tumbling over each other in a disorderly fashion. But in a time crystal, although each atom is still vibrating, they're doing so in a synchronized manner that creates the illusion of a static, unchanging structure. This strange behavior led some people to claim that time crystals are actually a new phase of matter, different from both solids and liquids and gases. But others argue that time crystals are really just a special type of phase in a fluid that can exist alongside solids and liquids. Either way, time crystals are definitely something new and mysterious. And here's where things get even weirder. When the team at Basel turned off the laser that was keeping their time crystal stable, they expected it to revert back to a normal liquid state. But instead, it kept its atomic dance for a full hour, which is an eternity in the world of quantum physics. After that, it returned to a normal liquid state, but not before dancing for the longest period ever recorded for a time crystal. What's going on here? Why would a group of atoms decide to move in perfect unison? And why does it seem like time slows down inside a time crystal? To understand how a time crystal works, we need to learn a little bit about quantum mechanics. According to quantum mechanics, every particle has a wave-like property called an oscillation. An oscillation is a periodic motion that repeats itself over and over again, like the swing of a pendulum or the vibration of a guitar string. And now remember that time crystal. Those atoms in the supercooled liquid that appear to be frozen in place are actually oscillating. But just like a guitar string, they're also vibrating in sync with each other. The reason the atoms vibrate in sync is due to a phenomenon called quantum entanglement. Entanglement is a correlation between two or more quantum particles that can be greater than any classical correlation. That means if you know the state of one entangled particle, you automatically know the state of the other particles, no matter how far apart they are. For example, if you had two entangled electrons, and one happened to spin up, you would immediately know that the other electron must spin down, even if it was on the other side of the universe. The catch is that quantum entanglement is extremely fragile and easily destroyed by environmental noise or interactions with other particles. But if you can keep it from breaking, it can create some pretty remarkable effects. In the case of a time crystal, the entanglement between atoms allows them to communicate instantaneously, even if they're far apart. This ability to communicate instantly makes it possible for them to synchronize their oscillations and form a repeating pattern. But why would they want to do that? And what does it have to do with time slowing down? Well, it turns out that forming a time crystal is actually a way for the atoms to save energy. By moving in sync, they create a collective state that's lower in energy than if they were all moving independently. Now, you might be wondering, why don't atoms always move in ways that save them energy? Well, typically they do, but a time crystal is an exception. You see, normally, if you have a bunch of quantum particles, they'll tend to spread out and fill a given space in the most even distribution possible. This is called a microcanonical ensemble. However, a time crystal breaks this statistical law because the total energy of the system is conserved, allowing for a special distribution called a tilted microcanonical ensemble. In a tilted microcanonical ensemble, the particles are still distributed evenly, but they also have a sort of memory of their past behavior. That means that even though the particles are still moving randomly, they also correlated with each other in a particular way that depends on the history of the system. This correlation allows the atoms to maintain a sort of order that persists over time, and that's why we say that time seems to slow down inside a time crystal. It's because the atoms are moving in such a unique way that defies our intuition about how fluids should behave. At first, scientists thought that maybe the time crystal was just some kind of fluke, but now there's evidence that they're actually a common occurrence in nature. Researchers have since found time crystals in lots of places, including nuclear magnetic resonance, quantum optics and condensed matter physics, and they've even been spotted in outer space. In 2021, astronomers studying data from the European Space Agency SXMM Newton Observatory spotted a huge time crystal of iron and magnesium atoms in the blazing hot plasma of a star called HD 222688. The star is nearly 900 light-years away and has a mass 7 times greater than our Sun. Its outer atmosphere reaches temperatures of over 10,000 kelvins. That's 9,727 degrees Celsius or 17,540 degrees Fahrenheit. And yet, somehow, under these extreme conditions, the atoms manage to synchronize their vibrations and form a gigantic time crystal. To put this into perspective, you'd have to cool a hydrogen atom down to about 10 picokelvins to achieve a similar effect. A picokelvin is 1/trillionth of a Kelvin. Of course, you and I won't be seeing any of these time crystals anytime soon. They exist in realms of temperature and energy far beyond anything we could hope to replicate here on Earth. But that doesn't mean we can't learn something from them. In fact, scientists are excited about the potential applications of time crystals. One idea is that time crystals could be used to create a new type of clock that's immune to hacking. Since time crystals are only stable in a narrow range of temperatures, any attempt to hack them would disturb the delicate balance of their internal structure, alerting the user to the attack. Another idea is that time crystals could be used to develop new types of quantum computers that are faster and more efficient. In the end, time crystals may turn out to be one of the most important discoveries of the 21st century. But as David Choi, one of the researchers who discovered the first time crystal, freely admits, we still have no idea how they work. That's right. Even though time crystals have been studied for more than 5 years now, scientists still don't fully understand how they function. It's truly amazing to think that there are so many mysteries left to be solved in our universe. Who knows what other strange and wonderful phenomena we'll uncover in the years to come. If you like optimistic science and text stories, stay tuned for more.